Myself, Dr. R Kesavulu, Associate Professor from Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the energy transfer from gadolinium 3 plus to terbium 3 plus ions in silicoborate glasses for green laser applications. This is one of the important topic from the laser glass spectroscopy. So last and previous session was discussed on the enhanced visible emissions of prismodium 3 plus doped oxyfluoride transparent glass ceramics. We discussed in last session introduction and experimental methods and techniques, and the resultant discussion of the prismodium 3 plus doped oxyfluoride transparent glass ceramics, and conclusion of the prismodium 3 plus doped oxyfluoride transparent glass ceramics. Today I am going to discuss about the energy transfer from gadolinium 3 plus to terbium 3 plus ions in silicoborate glasses for green laser application. In that we are going to discuss about the introduction of the terbium 3 plus ions in silicoborate glasses, as well as experimental technique and experimental methods. Finally, resultant discussion. Finally, we will conclude that conclusions. These are we are going to discuss about in the present study. So, main introduction: importance of lanthanide ions or rare earth ions. Among the periodic table, the lanthanide ions, these are black elements from lanthanum to lutetium. In this, we are going to discuss about the gadolinium and terbium. How energy transfer mechanism takes place from gadolinium 3 plus to terbium 3 plus ions. That we are going to discuss in the present study. So, electronic configuration of rare earth ions comes from the xenon and 4Fn to 5s2 5p6. That is a black element of the incomplete inner 4Fn orbital. That is we are discussing the rare earth elements in the black elements. What are the optical properties of rare earth elements? Strong absorption and fluorescence and a wide range of excitation levels and emissions from UV visible to IR infrared regions. What are the important applications of the lanthanum 3 plus doped rare earth elements in the glass materials? This is lasers, displays, sensor and lightings, biomedical imaging, and extra applications we are going to use for the lanthanum or rare earth ions in the glass materials. So this is we are the main introduction in the lanthanum 3 plus ions. So introduction of rare earth elements. The 4F and 5F black elements are their unique trivalent state of 4Fn electronic shielded by the 5s2 and 5p6 electrons, and so many advantages involved in the rare earth elements or lanthanide ions. So what are the glass? Glass is an indispensable photonic platform material due to its high optical transparency and thermochemical strength and ability to shape into an almost unlimited range of geometrical structure and compositions. These are the main important things of the glasses. What are the applications for the glass materials? So laser gain media. So it is one of the important application is laser gain media. Fiber amplifiers also can use. Just optical component, different kind of optical components you can make by use of different kind of laser glasses. There's medical accessories and massive structures and entertainment and extra. Entertainment means different kind of shopping mall. You can see the different kind of laser source. That kind of also you can use for the different rare earth doped laser glasses. So one of the particularly in the rare earth elements in glasses, what kind of applications we can observe in the rare earth elements? So many applications, that is mainly laser gain media. This is one of the important parameter while preparing the glass material. What kind of applications we can use means this is laser gain media. This is one of the important application. Just optical fiber amplifiers and different kind of solid state lasers we can prepare the different kind of rare earth elements or lanthanide doped silicoborate glasses. These are the introductions from the rare earth elements. What are the main introduction when the gadolinium and the terbium 3 plus ions in silicoborate glass? The oxide-based glasses attracted by oxide-based glasses activated by terbium 3 plus ions have demonstrated to be delightful candidate for the gain media in the green region. That is particularly in the terbium 3 plus doped glasses give the emission around at green region, that is 543 nanometers, since the 5D4 to 705 transition of terbium 3 plus doped material provides a 4-level laser system. Terbium 3 plus ions exhibit the 4-level laser system with lower threshold pump power to obtain strong green pulsed laser operation at 543 nanometer. This is one of the important application in the terbium 3 plus doped silicoborate because it's having the 4-level laser system at the same time with the lower threshold pump power. to obtain the strong green emission, particularly wavelength of 543 nanometer. This is useful for the green laser applications. You can use for the terbium-3 plus doped silicoborate glasses. Particularly, silicoborate glasses paved the significant advantages and improvement over the silicate and borate glasses. Here we are combined with the silicate SiO2. We are mixed with SiO2 plus B2O3. So boron trioxide and silicon dioxide both we are incorporated in the glass material. That is, you can call it as the silicoborate glasses. So in this particularly, these silicoborate glasses are considered to be suitable host for optically active ions because of their moderate melting point. So because silicate glasses having the melting point is very high. Whenever added with the boron trioxide melting temperature will be very low compared to silicon dioxide. Whenever mixed it together, automatically melting point will be decreasing. That is because of their moderate melting point. That is not high, not low. This average medium. That is moderate melting point, high transparency, and high thermal stability, low nonlinear refractive index, and good rare earth ion solubility. Besides, physical and chemical stability will be very high. Whenever silicoborate glasses have the important physical and optical properties. That is why we are concentrate or focus on the silicoborate glasses. They mix it two hosts, that is silicon oxide and borate. So that is silicoborate glasses we are preparing for the particularly terbium-3 plus dope silicoborate glass for green laser applications. Next, coming to the material selection. The spectroscopy properties and energy transfer from gadolinium-3 plus to terbium-3 plus ions in silicoborate glasses for green laser applications. We are studying the how energy transfer takes place from gadolinium-3 plus to terbium-3 plus ions. See, chemical composition of the terbium-3 plus dope gadolinium calcium silicoborate glass system is 55 minus X boron trioxide. There is a more concentration is more percentage is 55 minus X is boron trioxide, 10 mole percent of silicon dioxide, and 25 mole percent of gadolinium oxide, 10 mole percent of calcium oxide, and X mole percent of rare earth dope, that is terbium Tb2O3 ions. So hereafter referred as this glass is BSGD calcium Tb 0. Concentration low concentration from 0.01 to 0.05, 0.1 and 0.5 and 1 mole and 2 mole. These are the different concentrations of the rare earth elements doped in the silicoborate glasses. Here in particularly silicoborate, we have more concentration of mole percentage we are taking boron trioxide, and low concentration is 10 mole percentage and 10 mole percent calcium oxide, silicon dioxide, and 25 mole percent gadolinium oxide takes place. That is in the modifier. So that is why in this material it will energy transfers from the gadolinium-3 plus to terbium-3 plus. That we are going to study in the present study. That is why this paper shows the energy transfer from gadolinium-3 plus to terbium-3 plus ions in silicoborate glasses for green laser applications. So how the silicoborate glasses are prepared by using the melt quenching technique. The experimental technique is preparation of glasses. We are prepared by the conventional melt quenching technique. Instead of above mentioned these compositions, the 55.x, 10, 25 mole, 10 is concentrations of the chemical composition we are taking to the electrical furnace. First, initially, you need to take the weight of the total chemical composition. The total weight should be in the 20 grams. After taking the chemicals, we have put into the agate mortar for the mechanically we have to crush the powder for fine powder to grind up thoroughly in fine powder. After taking the fine powder, put into the platinum crucible and cover with the platinum lid. Then after filling the chemicals in the platinum crucible, we have to keep into the electrical furnace at the temperature of 1450 degrees centigrade. Time duration is 1 hour. We need to keep at the temperature of 1450 degrees centigrade for 1 hour. After melting the sample, we have to pinch, that is a preheated brass mold. We need to pour the, after melting the glass composition, we need to pour into the preheated brass mold at the temperature of 400 degrees centigrade for 2 hours. So after take it down the annealing temperature, why we are using the annealing is to avoid the thermal stress and strain, and we have to, after annealing 400 degrees centigrade 2 hours, we need to take it out the glass, prepared glass sample and cut the small pieces and send for the polishing and both side thoroughly and back and front. Then after taking the samples, we need to measure for the different characterization techniques. So what are the characterization we are going to measure in this present study of silicoborate glasses doped with the terbium-3 plus ions? That is, first one is absorption spectra. So per clean Elmer spectrometer used to measure the a lambda 950 model number, that is the wavelength range from the 250 to 2500 nanometer. Here observation spectra we are carried out by using the Flickr spectrometer in the wavelength range from 250 nanometer to 2500 nanometer. Next, fluorescence, excitation and fluorescence and decay time measurements were carried out by using the fluorescence, and lifetime measurements were carried out by using the Jobin ion fluorolog 3 spectrophlorimeter using xenon arc lamp as a radiation source by exciting the sample with 394 nanometer. So all the measurements were carried out at room temperature only. So all the measurements we need to carry out at room temperature only. Absorption, fluorescence and lifetime measurements. Next, first result and discussion, we are going to discuss about the absorption spectra. From the absorption spectra, I see the optical absorption spectra of the prepared BSGD, the 1 mole concentration of the silicoborate glasses. We are measuring the UV visible and in near infrared region. Instead shows the linear dependence of intensity of the 7F6 to 5D4, that is ground state 7F6 to excited state 5D4 level, that is 485 nanometer transition with the Tb3 ions concentration. So this absorption spectra shows the wavelength versus absorption coefficient centimeter inverse. So inside in a visible region, you are getting only one absorption, that is 7F6 to 5D4 transition. Remaining, we are getting two more absorption peaks from the near infrared region, that is 7X to 7F012 and 7F6 to 7F3. These are the near infrared absorption peaks. But in this inset diagram shows the terbium concentration versus this 7F4 to 5D4 concentration, how increasing the concentration, how the intensity will be changing at the particularly in the 500 nanometer, nearly 500 nanometer. This is the source the figure UV visible region. The only one absorption peak observed in the 485 nanometer. That is the 485 nanometer. That is the 7F6 to 5D4 transition. So in NI region, we are getting two absorption bands. That wavelength range is 1876, and other one is 2191 nanometer. Other due to transition from the ground state 7F6 to different excited state of the Tb3 ions. The inset figure shows the intensity of the 7F6 5D4 transition, that is 485 nanometer transition, with respect to different ion concentrations. As seen from the figure, the absorption intensity of the particularly in the 485 nanometer, the linearly increases while increasing the concentration of Tb3 ions. That is mainly indicates that the successfully incorporation of Tb3 ions and the present silicoborate glass matrices. That means it shows the intensity at a 485 nanometer absorption intensity will be linearly increases while increasing the Tb3 concentration. That is shows this indicates that the successfully incorporation of the terbium-3 ions in the present terbium-3 doped silicoborate glasses. Next, coming to the excitation spectra of the terbium-3 ions. See the excitation spectra of the present silicoborate glasses, different concentration of terbium-3 ions. We are monitoring at 543 nanometer. So we are emission monitoring 54 nanometer, and we are getting the different absorption peaks from ground state to different excited state. So we are getting the one is the intense absorption excitation band at 6A7/2, 6A9/2. That is mainly due to the gadolinium-3 So in our chemical composition, we have 25 mole percent of gadolinium-3 gadolinium oxide we are using. That is why you are observing the gadolinium highest intensity peak, particularly for gadolinium-3 ions compared to terbium-3 ions. That is why we are using the this 275. That is around 275 nanometer, 8S3/2 6 nanometer, and also 3 nanometer. That is associated with the worst bands of the gadolinium-3 ions. So here small bands we are observing. This is mainly due to the gadolinium-3. That is 275 nanometer is we are getting the very intense peak of the gadolinium-3 ions. And one more peak also observed from the gadolinium-3 ions. That is a less intensity compared to this both the intensities. This 275 nanometer. This 275 nanometer is we are getting the highest intensity for the excitation spectra of the silicoborate glasses. So these are the different transitions from the terbium-3 ions from ground state to 7F6 to different excited state levels. This is the different concentration of the terbium-3 ions. Among the all excitation peaks, the intense and strong excitation band peak 275 nanometer is used to investigate the emission spectra characteristics of the silicoborate glasses doped with terbium-3 ions. We are going to study the emission spectra by exciting or pumping of the 275 nanometer. This is mainly due to the gadolinium-3 ion. So this is the emission spectra of the terbium-3 plus doped silicoborate glasses. In this, the emission spectra exhibits two group of transitions. This is 5D3 level and 5D4 level transitions. So this is the 5D3 level transition of the emission bands of the terbium-3%. This is the 5D4 transition. So this ascent transition originating from the 5D3 and 5D4 states, ground state, and molecules of the 7FJ of terbium-3 plus ions. So and also additionally, one more emission peak was observed at 312 nanometer. This is, so we are observing one more additional peak at 312 nanometer. That is mainly transition belongs to 6p7 to 8a7 by 2. This is due to the gadolinium 3 plus ion present in the host matrix. So this is the source in the inside diagram. So these are the emission spectra of the terbium 3 plus doped silicoborate glasses. In that one, in host itself, there are gadolinium 3 plus ions present. That is why here we can study the energy transfer mechanism from gadolinium 3 plus to terbium 3 plus ions. So this is the variation of intensities. That is the gadolinium 3 plus intensity, particularly in 312 nanometer, and terbium 3 plus ion intensity at 54 nanometer. We are observing the two intense bands. One is due to the gadolinium 3 plus ions, that is wavelength at 312 nanometer. Other one is green emission we are observing at 543 nanometer, that is due to the terbium 3 plus ions. That is we are observing how energy transfer takes place from the gadolinium 3 plus to terbium 3 plus. See the concentration versus this black line shows the intensity of the gadolinium 3 plus ions, while increasing the concentration very low, we are getting, while low concentration we are getting the intensity will be very high. If increasing the concentration, the gadolinium intensity will be decreasing. But in the case of terbium 3 plus, while increasing the concentration, terbium 3 plus intensity will be increasing up to 1 mole concentration and slightly decreasing at 2 mole concentration. That is concentration pitching takes place particularly at 1 mole concentration of terbium 3 plus ions. But in the gadolinium 3 plus ions and low concentration, 0.5 concentration, we are observing the highest intensity and decreasing the, while increasing the terbium 3 plus ions. That is mainly due to the energy transfer takes place from gadolinium 3 plus to terbium 3 plus ions, that we are going to study in this emission spectra. See, the host material, that is gadolinium 3 plus, and dopant is terbium 3 plus. See, gadolinium 3 plus is mainly due to the host matrix, but terbium is dopant. Terbium 3 plus is dopant. So that is the energy transfer takes place from gadolinium 3 plus to terbium 3 plus, because if increasing the concentration, gadolinium concentration decreasing from lower concentration to high concentration. But in the case of terbium 3 plus, but increasing the terbium concentration, particularly in the case of 1 mole concentration of terbium 3 plus ions having the maximum intensity, and increasing the concentration, green intensity will be decreasing at 2 mole concentration of terbium. This is shows the there is a successfully energy transfer takes place from the gadolinium 3 plus to terbium 3 plus ions, that we are going to discuss in the energy level diagram. This is the we are observing from the emission spectra of the terbium 3 plus doped silicoborate glasses. Next, lifetime measurements are decay time measurements from the gadolinium 3 plus terbium 3 plus ions in silicoborate glasses. See, this is time versus normalized intensity. See, particularly we are studying the 5D4 level. That is, we are mounting the emission at 543 nanometer. That is a green emission. Pumping with a gadolinium wavelength, that is 275 nanometer. Because gadolinium 3 plus ions showing the highest intensity pumping is 275 nanometer. That is why we are using to study the lifetime measurements. We are pumping the 275 nanometer and mounting the emission wavelength and the decay times. We are measuring the emission of 543 nanometer emission. So 54 nanometer emission of terbium 3 plus, we are observing the lifetime measurements, different concentration from 0.01 to 2 mole concentration. We are studying the lifetime measurements. These lifetime measurements shows the almost all the concentration shows the single exponential nature. The decay curve exhibits the almost single exponential nature for the, all the concentration. We studied terbium doped silicoborate. The experimental lifetime is carried out by using the fitting of single exponential curve. So we are calculating by using that fitting. We are calculating the tau experimental value is low concentration having the 2.31 and 2.27, 2.24, 2.20, almost constant lifetime decay times is almost 2.3 milliseconds we are observing. So averagely we are getting 2.3 or 2.2 milliseconds. That means this shows the all the concentration of terbium 3 plus ions single exponential nature. There is no energy transfer in the particularly in the 5D4 transfer, but energy transfer takes place in the particularly in the 5D3 level, that we are going to discuss in the partial energy level diagram. So this is the CIE color coordinates of the terbium 3 plus doped silicoborate glasses. In this CIE color coordinates, we are calculated by using the in 1931 Commissioner International Ecological CIE established the universal qualitative model of color space. By using this theory only, we are calculating the color coordinates of the terbium-3 plus doped silicoborate glass. See the concentration. So here low concentration to increase in the concentration. See low concentration, that is completely transparent. So terbium-3 plus concentration will be very low. So it will be transparent, no color visibility. After increasing the 0.5 and 1 mole and 2 mole, the increase in the concentration of terbium-3 plus ions, the color will be green color. We are this is a pumping of the UV lamp. So the photographs of bright green emission under the ultraviolet lamp excitation, we are getting the color visibility from the transparency. So white color to increase in the green emission. So color coordinates mainly confirm that the terbium-3 plus doped glasses shows the green color. That is why you can use for the green laser applications. You can use for the terbium-3 plus doped silicoborate glasses. These are the color coordinates. We are calculating the color coordinates value by using this theory. Actually, we are color coordinates. We are using the terbium and intensity from emission spectra only. We are calculating the by emission spectra. The highest emission in the terbium-3 plus doped silicoborate is 543 nanometer emission. This highest emission. By using this highest intensity only, we are calculating the color coordinates. That is particularly each and every color coordinate value fall into the green region. That is why this terbium-3 plus doped glasses we can use for the color display devices, particularly in the green color display devices we can use for the terbium-3 plus ions in silicoborate glasses. So these are the color coordinates. Next, partial energy level diagram and the energy transfer of the gadolinium-3 plus to terbium-3 plus ions in the particularly in BSGD calcium terbium glasses. So this is the energy level diagram of the gadolinium-3 plus. In gadolinium-3 plus ground state is 8s7/2 to different excited state of the 6p7/2 and 6a1. So here the gadolinium-3 plus we are getting the two absorption bands in the gadolinium-3 plus, that is 275 and 312 nanometers. So we are exciting the 275 nanometer energy transfer takes place from the 275 to 213. This we are getting the emission peak. But same energy we are pumping the energy transfer from gadolinium-3 plus to terbium-3 plus ions from this level to this level. That means this both energy levels will be both are similar. That is why this energy transfer takes place from the gadolinium-3 plus ion to terbium-3 plus, because these two energy levels and these two energy levels are almost equal. That is a cross relaxation channel, CR. See here, this is the CR with cross relaxation. Here and here, both are similar, same energy bands. That is why energy transfer takes place from gadolinium-3 plus to terbium-3 plus ions, and terbium-3 plus ions and different emissions we are observing. This is 5D3 emissions in the blue emission and 5D4 green emission. We are observing the blue emission and green emission. By using the blue and green emission only, we are calculating the previously color coordinate system. By using the color coordinate system, each and every concentration of terbium-3 plus ions shows all the color coordinates will fall in the green region only. That is why you can use for the color display device applications. By energy transfer mechanism also, we are measuring the emission channels of the blue and the green. In particularly 543 nanometer, we are getting the intense and strong emission, and particularly 543 nanometer. That is mainly useful for the green laser applications. Next, conclusions. So this is gadolinium calcium silicoborate glasses doped with terbium-3 plus ions have been prepared and characterized with their physical, thermal, and optical and luminescence properties. From the excitation results, we observed the strongest excitation bands 275 nanometer and 312 also we are observing. But among the two excitation bands, 275 is the strongest excitation for gadolinium-3 plus ions, and is generated the emission of terbium-3 plus ions through energy transfer from host matrix to activator. The activator here is terbium-3 plus ions, that is dopant. So this emission spectra of the silicoborate glasses exhibit weak blue emission, that is a 5D3 to 7F3 to 7F4, 7F5, 7F6, and the strongest green emission is 5D4 to 7F3, 7F4, 7F5, 7F6 under excitation of 275 nanometers. So we are observing the weak blue emission and strong green emission. That is why this terbium-3 plus doped glasses used for the green display device applications. The decay times of 5D4 level exhibit single exponential nature for all the concentration of terbium 3 plus ions with a small decay time variation from the 231 nanometer to 2 the averagely 2.2 milliseconds we are getting for the terbium 3 plus dope mounted in the emission of 5D4 emission means 543 nanometer emission. Thus lifetimes. The long decay time of the 5D4 level could reduce the pump threshold to get the good laser emission, particularly at 543 nanometers. That is the useful for the terbium 3 plus ions. Finally, therefore, the present results suggest that the terbium 3 plus dope and silicoborate glasses could be a potential candidate for green color display devices as well as solid state green laser applications also we can use for the terbium 3 plus dope silicoborate glasses. These are the conclusion or summary of the present study. Next, finally, references. These are the references cited in the particularly in this work. This work is mainly published in the Journal of Fluorescent Compounds in 2017. This is 2017. This published. This is one of the my publication. This is the energy transfer from the gadolinium 3 plus to terbium 3 plus ions in silicoborate gases, particularly in the green laser applications. These are the references for the present study. Finally, thank you. So next class will be continued in the next section. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.